system in the smart energy domain. And we have developed an integrated approach to simulate these models, but also to verify them or to synthesize policies, strategies, or controllers to achieve many certification objectives. We use models that are both hybrid, as I mentioned before, namely appropriate for cyber-physical systems, as well as stochastic. Stochasticity is in particular used to model uncertainty. And uncertainty can come from various aspects, the way that these buildings are used, or perhaps the dynamics of weather. We have tool support, so we've developed in particular two toolboxes, Faust and Stokey, that do these verification and synthesis, as well as simulation goals. We have also developed a few studies in synthesis of predictive maintenance actions, and this is what I'm going to talk about in the context of today's talk. So here's a first intro about biomass boiler. So we have boilers that build biomass like pellets, for example, hopefully not coal or wood, and they generate heat. The functioning of such biomass boilers leads to the buildup of soot, namely black powdery dirt, which clogs pipes of these biomass boilers, and that leads to decrease in efficiency of their operation. Maintenance ought to be done, and it ought to be done in a couple of ways, either by cleaning these pipes, or perhaps at times by replacing parts of the overall biomass boiler device. And in particular, this cleaning can be done by high pressure blowing of some liquid within the pipes. So it's interesting to know that cleaning and maintenance or replacement can be done either online or sometimes offline. Offline means that you have to stop the biomass boiler, take it offline, replace your part. Cleaning can be done both online and offline, and this will have some repercussions, as we'll see in a few slides. So the goal of this talk is to compute an optimal, and I'll tell you what optimality is, cleaning or replacement strategy or policy or control that minimizes overall costs. Costs will comprise the operational costs, so how much it costs to operate such a biomass boiler, as well as maintenance costs. So we'll need to find a trade-off between them. Later, I'll also introduce discomfort costs, namely costs to the users of these buildings. Will comprise a model with two variables. One, eta, will encompass the performance of the biomass boiler, or equivalently, or dually, I would say, the degradation of its operation. The second variable will comprise demand, so heat demand, which evidently depends on the outside temperature and humidity. We'll build a model that is fed from data, and will synthesize in a closed loop a controller that affects the dynamics, the evolution of this model. And the synthesis will depend on a cost, again, which will comprise maintenance and operation. The way that we will synthesize this controller or this policy, this synthesis, is through these models and through an optimization approach called dynamic programming. Many of you will be familiar with it, which I will explain next. So it's a sort of recursive, backward recursive approach that leverages some Bellman iterations. For those of you that are familiar with this, it should be quite clear. I'll describe them in a few slides. So what I'd like to do now is describe the dynamics of this model, in particular dynamics of the two variables of this model, the demand, Q out, and the performance or the degradation, actually, eta. So the model of the demand, well, we developed actually a bunch of models. So this is the simplest one. It's fed by yearly data, so historical data. This is this tilde Q out function, which is here represented by these red dots. And it has a regressive an autoregressive feature, namely it has a one-step memory. So the demand at the next time step, or the next whatever is the time step, whether it's a week or month, is a function of the current demand plus the sort of historical data that comes in, right? So it has a one-step memory. It's a very simple model. Evidently, we built higher order models with larger memory in case, for example, there's some periodicity in the demand. And this will be a more complicated version of this first order model, autoregressive first order model that I just described. So the takeaway point for this simple model of demand is you have historical data, you can punch it up, you use it to build a model for demand. And as you expect, this model will give you more demand in the middle of the winter, less demand, if at all, during the summer. And in particular, will give you no demand, say, during the Christmas break, as you can see here from the data we have. The second part of the model comprises the efficiency. Actually, eta is a parameter that encompasses that. So the efficiency can go from a minimum to a maximum level, usually between 0 and 1, respectively. And the efficiency is updated across time, time being, again, either every week or every month, depending on how granular your model wants to be. In a way that is, again, autoregressive, so it has a one-step memory and depends on whether or not you have made a maintenance action. So action is UN and tells you whether you have made maintenance or not. In particular, in this case, we assume that whenever we do maintenance, we bring the efficiency up to the maximum level. Otherwise, if we don't do maintenance, then depending on how much demand there is, our efficiency decreases in time with a parameter alpha that we have fit, that we have regressed from data again. So the idea is that if the demand is high, then the efficiency decreases. There's more suit building, if you will. If the demand is low, then the efficiency doesn't decrease. In particular, if it's equal to 0, then the efficiency is the same because the biomass boiler isn't used, right? Again, very simple first order model for the dynamics of efficiency, or if you will, for the dynamics of degradation, which is the dual, you can think of this parameter. And that is built on data, in particular on historical data, which we have used to fit this parameter alpha. So these are the models of the dynamics. Evidently, the dynamics depend on whether you do maintenance or not. So this is where the feedback comes in. If we build a controller that performs this maintenance, depending on the evolution of this model, evidently this controller affects the dynamics as expected, right? Great. If we want to synthesize a controller, we need to have a goal, a task, or a cost. If you have a cost, you want to minimize such cost. Such cost is a monetary cost that encompasses two components, an operational component and a maintenance component. The operational component is how much it costs to operate this biomass boiler. And in particular, if you have high degradation or low efficiency, so if this parameter eta is low, you're expected to pay more because the biomass boiler isn't very efficient. So you have to exert more input, if you will, to heat up your environment. The pipes are clogged, right? Intuitively. On the other hand, you have maintenance costs, which are incurred not continuously, that is every time you operate the biomass boiler, but only once in a while, when you do replace or clean, if you will, the biomass boiler, in particular when you do exert a maintenance action. So notice that here we have a cost and dynamics that encompass two time scales. We have operational costs that you incur every time you use a biomass boiler. So in particular, every week, if week is the granularity of your model, and the maintenance costs, which happen only once in a while, maybe once a year or maybe twice a year, I don't know. So it's a model with different, if you will, granularity, different time scales. Evidently, attuning these two costs is key, right? Because The overall cost is just the sum of these two components. So here you see that the overall cost row is the sum of the operational cost, first term, and the maintenance cost. The operational cost has a fixed amount, which is called P-in, is proportional to the demand. So if there's more demand, you pay more. And it's inversely proportional to the efficiency. So, or rather to the degradation eta. So the smaller the efficiency, the higher the cost, right? The maintenance cost is very easy. You incur it only when you do maintenance, right? So, so it might happen once or twice a year again. Whereas this first term is something that you encounter whenever you have demand, whenever the biomass is operational. I hope that this is clear. This is the cost that we use. Now, if we're given the dynamics, if we have a control structure, in particular a feedback control structure, and a cost to minimize, then we can solve an optimization problem to synthesize an optimal control action, which is a maintenance action. That is predictive because it looks ahead over a particular time horizon. In fact, we can unfold these models as far ahead as we want. Evidently, we need to trust that the model is good. We fit historical data to that model. And so we need to be careful to maybe unfold it ahead of time, but perhaps synthesize a control and apply it only for a few time steps, maybe a few months, and then maybe update the model, namely update the parameters that we've attuned to the historical data that we keep on accruing that has changed, right? So in the application of this control that we synthesize can happen in a so-called receding horizon fashion. It's a kind of like an MPC, model predictive control approach. Intuitively, these syntheses can be done with dynamic programming. Dynamic programming boils down to take a value function and update it backwards in time. The value function is updated at the end, usually with no cost, because at the end of your time horizon, you perhaps have only a final step operational cost. And then you update it backwards in time by looking at how the dynamics affect, how the control affect the costs at every time. So in particular, if you do no action, say that your demand decreases at the next time step. If you do no action, then your performance will degrade. If instead you do a maintenance action, your performance will increase, in particular go to the maximum. So these updates are also known as Bellman iteration. Standard, this is not anything new in the literature. We just leverage this optimization approach to synthesize our control strategies. So here's an output of these predictive maintenance actions over a few years. So we've unfolded the model over a few years. The model is periodic, and you'll see this reflected also on the maintenance actions. So it's yearly, if you will, periodic with a yearly time period. Here you see efficiency on the vertical axis and time on the horizontal axis. Yellow means do maintenance, blue means no action, no maintenance. Intuitively, this is very explainable, very interpretable. If the efficiency is below a certain level, in specific moments of time, in particular in the middle of the winter, then you ought to do maintenance. Whereas in the middle of the summer, for example, which is when you see these blue sort of columns, no maintenance is needed. Here in particular, you see that within the yellow column, there is a kind of like a blue line, and that corresponds to the winter break. Since there is no demand, then no maintenance is needed, really, at that particular point in time. Evidently, this is all periodic because it trusts a model that is periodic. As I said before, you may not want to implement open loop your control architecture for 5 years, but just do it for a few months, then recollect data, update your model, and then synthesize ahead of time. in a so-called receding horizon sort of fashion, as I said before. Also notice that at the very end, there is no maintenance applied. That is, it's not worth to pay at the very end to improve the performance of the biomass boiler. If you're going to use it only for 5 years and you're towards the end of its lifetime, just suck it up and finish using it and don't maintain it. I hope this is an interpretable output. Great. So we've compared our approach, which is in the first line and based on dynamic programming, against other approaches like doing no maintenance, rather dumb. After a while, everything gets clogged. And of course, you pay much more using a crappy biomass boiler. Annual cleaning boils down to 5 actions over the 5 years. And of course, you don't do maintenance, but evidently the performance decreases, doesn't work as well. Let's do it every 6 months. That boils down to 10 actions, 10 times doing maintenance, as opposed to the 13 that we synthesize with our technique. It still costs more. Evidently here, the performance is always higher, but you pay more to do maintenance. Well, let's do it every 4 months, which leads to 15 times, which is close to the 13. You still pay more. So you see, there's this nice trade-off. The bad thing about doing it just in a way that is timely is that you don't know when to do it. I mean, if you do it every year, when would you do it? In the middle of the winter, middle of the summer, you don't know it. Well, it's better to rely on a model that is kind of dynamic, that will tell you when to do it, when it's needed, right? So I hope that these outcomes make sense. Evidently, the overall setup is limited. In particular, you can think of extending the approach in a number of ways. So first of all, I didn't tell you whether the maintenance can be done online or offline, right? So in particular, this can be actually modeled by thinking that when you do maintenance, discomfort might increase in the sense that you need to take your biomass boiler offline, you need to turn it off and we assume that it takes up a day to do maintenance. Likewise, if the biomass boiler is underperforming, then evidently it takes longer to warm up and people are colder, essentially, right? So there is a certain discomfort that is related, that is a cost on users, right? So can we try to monetize discomfort, which encompasses also, whether we do maintenance online or offline? So we try to do that. So there is here a new cost, which encompasses a final term, which has a fixed discomfort cost. This is tricky to find. It needs to be a cost that is well aligned with the other 2 components, the maintenance and the operational costs. And that depends, excuse me, on this discomfort time factor. This discomfort time factor is something that we computed as follows. We introduced dynamics of the temperature on a daily basis. We assumed that there is a certain temperature level which is related to being comfortable, say around 20 degrees Celsius. And let's say that whatever is your temperature at the beginning of the day, you get to this comfort zone, quite literally, in a certain time, which I think is called here T1. Now, if the biomass is underperforming, it will get there at a time T2, which is later. Now, the difference between these 2 times needs to be proportional to how much discomfort there is, right? In particular, yes, please.
The time is a little bit running out, so just give it 1 or 2 more minutes, please.
Will do. Thank you. Thanks for the heads up. I'm not keeping track. Thanks. So in particular, if your initial temperature is within or the comfort band, then you're done. Otherwise, you need to account for these discomfort costs. The second extension we've looked at is that you can either fix the biomass boiler or clean it. And in particular, the clean it doesn't improve it to a maximum performance. So here's a nonlinear function that tells you how much the cleaning affects or increases the performance of your biomass boiler. So now you will have 3 actions: replacement, cleaning, or don't do anything. we set up the dynamic programming approach, and we compare the outcomes of these sort of three-pronged maintenance approach, whether there is discomfort or not. So on the right-hand side, we don't use discomfort. And here, essentially, the interpretation of the output is that if the performance is lower than a certain level, then you have to clean. If it's really low, then you need to replace it. If you introduce discomfort, you'll see here these thin lines. It will tell you, well, you can only do maintenance when there is a weekend, namely when the users are not there. Because if you do cleaning or maintenance during the week, then the discomfort grows. There is more cost, not worth doing it. So with discomfort, actually, we can do scheduling of maintenance that is better, improved, more realistic. And in fact, we can argue that we reduce the discomfort costs. The tricky part of this approach is how to monetize discomfort and how to come up with essentially a trade-off that allows us to compare reasonably the discomfort costs with the maintenance and with the operational ones. Here's the end of my presentation. I have not talked about reliability via fault maintenance trees, something that others might discuss this afternoon. But I hope, as a takeaway point of my presentation, that now you know everything about this beautiful area of biomass boilers. Thank you very much for your attention.